Welcome to UVU CS3060 Lecture 8.4, where we discuss deadlock detection. So, deadlock detection is not like prevention or avoidance. Prevention, you're looking ahead to see if there's anything that can be done to eliminate the deadlock. And prevention is done during the actual running of the requests, where it's checking to make sure the system remains in a safe state. Deadlock detection allows the system to enter a deadlock state. So this is after the deadlock has happened. There are algorithms that help detect a particular deadlock. And once you've detected a deadlock, a scheme must be implemented that allows you to recover from that deadlock. So when it comes to the deadlock detection, we usually there's a couple of ways that this can be done. The first is using a single instance, or is during the single instance of each research type. We maintain what is called a wait for graph. In effect, all nodes are processes, and what each node and which each direction is we have a particular process waiting on another process. We're in effect eliminating the resource in between it and saying process I is waiting for process J. Now, periodically, an algorithm is invoked that searches for cycles in this graph. So you can tell this is like a resource allocation graph without the resources. If there is a cycle, there exists a deadlock because you'll have processes waiting in that cycle. An algorithm to detect a cycle in the graph requires an order n square operations. So this is a rather expensive operation, and there really isn't an easier way to search this graph. So you can see here a resource allocation graph and a wait for graph. So the resource allocation graph, it's not necessarily very easy to look for cycles here. But if we take a look at the wait for graph, the wait for graph eliminates a lot of hassle to find cycles, and we can actually see several cycles here. There's a cycle here, there's a cycle here, or the cycle around here. Now, if we have a process that terminates, so you'll see that process 5 is not waiting on anything. So if process 5 terminates, process 2 is now waiting for process 3 and process 4. And so we see that there continues to be a cycle even after process 5 has terminated. Now, if there's several instances of a resource type, well, we use the banker's algorithm again. Remember that the banker's algorithm uses available to determine the number of resources available, what is allocated from each process, and any requests that are being made by a particular process. And then the banker's algorithm is what's used as for the detection. It goes through, uses work and finish, as it was before, goes through and finds a process that can't have its resources allocated. And if we find that there's a process that is not able to finish, then the system is a deadlock state. And this is only after we've gone through all of the processes and checked. Now, in order for this to work, this also is an n squared times m operation. So banker's algorithm, or this detection algorithm, is very slow when it comes to deadlock detection. So here we have an example. We have 5 processes. Again, we have 7 instances of A, 2 instances of B, and 6 of C. And this is what's currently allocated by this particular system. Now, notice that there isn't a max. The original banker's algorithm had a max column, but in this particular case, we have what is allocated and what processes are currently attempting to allocate and waiting for. So there is nothing available, but can a process finish with a nothing available? Well, certainly. We have process 0, which is waiting on nothing right now. So we can take its allocation and add it back to available, which gives us 0, 1, and 0. Is there a request that can have that met? Well, process 2 is also not waiting. So we have 0 here. We can add its allocation, 303, back to the available. Now we have 3, 1, and 3. And we've eliminated processes 0 and 2. Now can any process complete? Yeah, let's choose process 1 here. Process 1, or process 3, I mean. Process 3 has one request, and it certainly can be met by this 313. So we take all the allocation for that process and add it to the available, which brings us to 524. Well, at this point, we have process 1 that can have its allocation added back, and then finally process 4, which can have its allocation. So the sequence process 0, 2, 3, 1, and 4 shows that this system is currently not in a deadlock state. There are no cycles. So here we have a request that's made for process 2 is requesting an additional instance of type C. So now we have a request that there's clearly no resources available, which means process 2 will block, and process 2 is asking for C. So is this system in a deadlock when this request is waiting? All right, now, so what we do is we take a look to see if this request put the system in a deadlock state. Well, if we take a look, we see process 0 can terminate, but when process 0 terminates, it does not restore enough resources to meet any of the requests. Remember, process 0 has an allocation of 1, but nobody's looking for one resource of B. None of the other processes in process 1 through 4 is looking for that. And so all these processes, 1, 2, 3, and 4, consist of a cycle that is we have, and thus we have a deadlock state. So how often do we use this detection? It really depends on how often a deadlock is likely to occur, and what we do, and how many processes need to be rolled back. Because we really want, if we want to run this algorithm efficiently, we don't want to run it every single time. Remember, it takes order m times n squared to complete, and that's considered very slow. So when we have, if we do this at any given time, there may be cycles in the resource graph, and so we would not be able to tell which of the processes caused the deadlock. If we were to do this for every allocation, it would be slow, but we can know which process caused it. But if we want to only run this particular algorithm occasionally, it's not going to give us enough information to identify which process actually caused the deadlock. So now the question is, who do we terminate? Which process ends if we are just arbitrarily running our detection algorithm? Well, one option is just simply to kill all the processes that are deadlocked. That would certainly free up the deadlock, and it is fair because all processes would restore their resources back to the available list. We can also try to abort one process at a time. But which one do you start with? What order do you do this in? Well, one way is to use the priority of the process to determine, or how long processes have computed, how long they've worked, how much longer they have to completion, the resources that are used by the process. Do you free up the ones that are using the most resources, the least? How many processes will need to be terminated? You can also decide based on whether this is an interactive process or a batch process. So usually the way this is done, to select a victim, we really want to minimize the cost. What is meant by cost? Well, the cost is usually how many resources that particular process has, how long it's been running, its priority. We usually want to choose processes to preempt in order to from the least cost as possible. Perhaps there's a way to roll back the allocation requests. Maybe we can return to a safe state by moving a process to a previous state. There's also the case of starvation. Some processes may always be picked as a victim, which means that process will get terminated. It'll try again. It'll get terminated. It'll never complete because it's constantly ending up in a deadlock state, and it ends up having the least cost. This brings us to an end to Lecture 8.4, where we discuss deadlock detection.